Good afternoon. This is Andy Bechtolsheim from Arista Networks. I want to talk about the transition from 400 gig optics to 800 gig and 1.6 terabit optics in the next couple of years. To jump right in here, these transitions are fundamentally driven by the underlying transitions in SERDES I/O speed coming off the switch silicon. Today, the majority of switch silicon is either 25 gig NRZ still or 50 gig PAM4 electrical lanes shown in gray and yellow on this chart. Starting next year in blue, the 100 gig SERDES is starting to ship and reaching much higher volume in 2023. In fact, the projection is that the total bandwidth shipped in 100 gig lanes in 2023 will exceed the entire bandwidth of all shipments in 2022. And then in further out years, 24, 25, you can see the little green color coming in on top, which indicates the expected early shipments of 200 gig SERDES I/O. Now, the 100 gig SERDES speed directly drives 800 gig optics in the 800 gig 8-lane optical formats. Now, to be clear, the initial focus here is on dual 400 gig and octal 100 gig breakout applications. Separately, there is a 800 gig Ethernet spec that was completed by the Ethernet Technology Alliance in April of 2020, which will be incorporated in switch silicon starting in 2023. And this may be the first time in history that the 800 gig optics are ready and in volume production before the 800 gig Ethernet is available in the market. This slide looks back at the expected transition from 400 gig to 800 gig optics on a bandwidth basis. And as you can see, the 400 gig shown in blue is still ramping strongly for the next 2 years and is likely to peak out in 2023 when the 800 gig optics shown in green kick in. And then it is expected that 800 gig optics will be the majority of the shipments starting in 2024. Now, why is it so predictable that 800 gig optics will take over? It's very simple: lower cost, lower power, and higher density. And all of these are, of course, key issues in the marketplace for system vendors and customers alike. This is a list of expected 800 gig optics modules available in 2023. Starting on the top, 800 gig CR, which is in design, expected to deliver reach of 100 kilometers and more with 16 QAM modulation. The 10 kilometer version known as 800 gig LR, 100 gig FR4 and DR4 using 200 gig PAM4 optical Lambda, and then the FR8 LR8, which is a single fiber with 8 channels of 100 gig Lambda, the dual FR4, dual LR4, which is the 400 gig breakout application, the DR8, which breaks out into 8 channels of 100 gig, and also SR8 based on VCSELs to break out in 8 SR channels. All of these optics are expected to be in the market in 2023, and many of them actually are in the lab today. I mentioned breakout applications. The majority of initial use of these 800 gig modules will be exactly that. People want to have bigger radixes on their switch chips. They want to do shuffles and better fault tolerance. And so it's absolutely key for the optics module to support the standard industry standard connectors that go along with these breakout applications, in particular the dual LC and the dual mini LC, the dual MPO. And also for the 800 gig DR8 and octal breakout into 8 SN or MDC connectors. This shows an OSFP module with either dual LC or dual mini LC. And on this chart, we're showing the dual MPO and the octal SN MDC connectors. All of these fit on the front surface, on the front cross-section of the OSFP module. In the lab today, we have modules from at least 6 different vendors shown on the right that have these breakout capabilities. And we're making good progress in qualifying these modules, and they should be available in the market by the end of this calendar year. This is a picture of the next generation 51.2 terabit switch with 64 800 gig OSFP modules, which will support up to 128 400 gig ports in a 2U form factor. And one more chart from a different analyst firm called Light Counting, which projects the optic sales to the large cloud companies, and again illustrates how the 800 gig modules shown in orange will be the majority of the revenue starting in 2024. Now, next topic, 200 gig Lambda optics. There's a lot of interest in increasing the speed per Lambda because, again, this promises significant power reductions, maybe 20 to 30%, significant cost reductions, and obviously it is the best choice for the future 200 gig electrical lanes expected on the 102.4T switch silicon. Now, to give you an idea of the potential cost reduction here, if one were to take a 800 gig DR8 module that's just in the lab today and compare it to the next generation 1.6 terabit DR8 module with 8 by 200 gig Lambda, what you would find is exactly the same component count, meaning the same number of lasers, the same number of modulators, the same number of fiber terminations, connectors, and so on. So fundamentally, the BOM structure cost supports a very significant cost reduction per bit between the 100 gig generation and the 200 gig generation. The status of 200 gig Lambda optics is in early development. I think it's fair to say that technical feasibility is established at this point. There's multiple optics technologies that are capable to perform at this speed, including EML and silicon photonics. What we do need as an industry, though, is a complete 200 gig Lambda specification, which does not exist yet. Basically, we need a new forward error correction and the precise optical specification for these links for the industry to really be able to tape out and deliver these components. One model for 200 gig Lambda adoption is that the first of these modules will show up in late 2023 and gather some momentum in 24 and then achieve much higher volumes in 25 and beyond. 100 gig Lambda optics are clearly going to be the high volume probably through 25, 26, if not beyond. Now, let me turn to the 1.6T pluggable optics modules. And this is basically the idea of taking the 8-channel modules and running them at 8 by 200 gig electrical lanes, which works pretty well for the OSFP. The work on this has started almost a year ago. There has been a working group looking at this in great detail, and the conclusion is this is not only feasible, but this can be achieved with some minor adjustments in mechanical dimensions, and all of this will be fully backwards compatible with the existing 800 gig OSFP. Now, the thing though is that these 200 gig the 200 gig electrical lane modules are inherently tied to 200 gig SERDES switch silicon, which is currently expected to be in production in 2025. Whereas the 200 gig Lambda optics are actually available much sooner, perhaps as early as second half of 2023. And there's some interest in the industry to bring 200 gig Lambda optics to the market as soon as possible, given the potential cost and power savings. So to enable that in the context of a low-cost module, we recently introduced the OSFP-XD, which stands for extra density. And this module has 16 100 gig lanes, basically a second row of connector pins to double the lane count. And this enables to deliver a 1.6 terabit module in conjunction with the 51.2T switch silicon in 2023. And what is amazing is that it's the same density on the front panel on the module side, which means that the 51.2T density will fit into a 1U line card or 1U fixed chassis. And if the power allows, it is conceivable that a 102.4T density with a 200 gig Lambda and 200 gig electrical interface will still fit into the 1U form factor a few years later. So again, this is 16 electrical lanes of 100 gig, and to get to 1.6 terabits, it would be 3.2 terabits with 200 gig SERDES interface. The power is specified to go up to 33 watts, which is needed to support the coherent applications. And one thing that's very important here is the footprint of the connector cage of the OSFP-XD is identical to a stacked 800 gig OSFP, which means that system vendors can design a single motherboard that can be configured with either a stacked 800 gig OSFP connector or the 1.6 terabit OSFP-XD. And we do believe this will greatly accelerate adoption. The kind of modules we expect to see in the 1.6T form factor includes 1.6T ZR modules, the LR version that has a 10 kilometer reach, CWM8, which would be 8 channels of 200 gig PAM4 over duplex fiber, dual FR4, which would be 2 800 gig Ethernets with dual LC connectors, and DR8, which is 8 channels of 200 gig Lambda breakout. There's also some interest to do 16 channel 100 gig Lambda interfaces as well. In terms of advantages, the OSFP-XD is the densest pluggable optic solution on the market today. Most importantly, it matches the density of future switch silicon on a 1U front panel basis. It also supports the full range of optics technologies from 100 gig Lambda, 200 gig Lambda, and coherent. And of course, it retains all the benefits of pluggable optics modules in terms of configurability, serviceability, and technology flexibility. Now, let me switch gears and talk about power and how we can reduce the power of the optics. So what's happening is the bandwidth in the cloud is growing very rapidly. Industry estimates peg it to 50 to 60% growth per year. At the same time, there is a power reduction on the optical side and the network switching side in the range of 25 to 30% per year. But clearly, the overall power of the network is increasing, given the fact that the increase is larger than the decrease in power per bit. Now, to reduce power, the most predictable thing is to use the most advanced process technology. The expected power reduction from 7 nanometer to 5 nanometer to 3 nanometer is quite significant. It's almost a factor of 2 over the 2 generations. And again, this is very predictable based on the physics behind that. Now, the power reduction here applies to both the switch chip and the DSP and the optics. And I'm showing here estimates for projected power for the 25.6T switch, which is in 7 nanometer technology, the 51.2T switch in 5 nanometer, and the future 102.4T switch in 3 nanometer technology. And as you can see, the total system power, switch chip, fan power, optics, declines not quite by a factor of 2, but almost a factor of 2 over these 2 generations. Dialing down on the optics here, the 400 gig DR4 which the first generation did not have integrated TIAs and drivers, had a fairly high power per bit. The 800 gig DR8, which will use more advanced process technology for the DSP, so this is expected to be 5 nanometer here, and also vendors are integrating the drivers, is providing a significant power reduction. And then on the 1.6T generation, in hopefully 3 nanometer, we expect to see further power reduction as well. This is the same data in a sort of graph form. Now, the power per bit is declining. However, the power per module is increasing because obviously we're doubling and quadrupling the bandwidth per module. So the current estimates for 1.6 terabit data center modules range between 20 and 25 watts. And for the coherent DCO modules, go up to 30 watts per module. To reduce the power further, we do need 3 nanometer and beyond that 2 nanometer DSPs. They do provide a significant power reduction on the digital side, including for the coherent DSPs. There's also opportunity to design lower power SERDES, and one should definitely not bet against the ingenuity of those engineers to drive power reduction. And of course, there's optics technologies, including lower power modulating technologies that will reduce the laser power required. To sum this up, there's lots of innovation ahead here on the power side. 200 gig Lambda will reduce power, better laser sources, lower coupling losses, lower loss modulators, all help to reduce the power. Now, it's hard to predict exactly where this will lead us. In discussion with various industry vendors, my belief is the industry can achieve 5 to 6 picojoule per bit in 5 years. So that would be in 2026, between a combination of more aggressive DSP technologies, much better reducing coupling inefficiencies, more efficient laser sources, and reduction in modulation losses. Now, importantly, all optics benefit from power reduction. So power reduction on the technology side is independent of the form factor. So it's not a function of pluggable or co-packaged optics. But what is true is that pluggable optics modules enables advances in lower power optics to be delivered to the market immediately into high volume shipping platforms. Whereas in the co-packaged world, that would be more difficult because you have to synchronize it with the release of a co-packaged platform. In summary on power, switch power per bit is declining significantly, almost a factor of 2 for every 2 process generations. Optics power also declining significantly, roughly a factor of 2 for every 2 process generations. And however, the power per optics module increasing due to the fact that it's doubling and quadrupling in capacity. I mentioned the power targets before for the 1.6T modules ranging from 20 to 30 watts. This means the industry needs a robust thermal form factor for these modules, and we do believe the OSFP has significant advantages there. But all said and done, there needs to be ongoing focus on further power reductions that we have discussed. Now, what about co-packaged optics? I think the best way to describe co-packaged optics right now is a work in progress. A lot of progress has been made. There have been numerous contributions by Facebook and Microsoft to the OIF, and for many other parties. There have been prototype developments and prototype demonstrations. The challenges are also well understood, which include laser power, optical losses, connector issues, manufacturability, repairability, serviceability, and so on. Now, the initial driving force behind co-packaged optics was, in fact, the belief that it could help to reduce the power on a switch chip basis, on a system basis, by up to 20%, largely by reducing the electrical lane power, the SERDES power, from the high power LR SERDES that's being used today to a much lower power XSR SERDES for the short reach between the silicon chip and the modulator. Now, the problem here has been that nobody has actually taped out an XSR SERDES switch chip or even optics DSP chip. And as a result, those power savings are actually not available as of this time. What has happened instead is the silicon vendors have developed so-called VSR or very short reach modes, which are not as low power as the XSR, but they have delivered significant power reductions up to 180 watts at the wall plug level for a 51.2T switch versus the more traditional LR SERDES. I'm illustrating this in this slide where the blue color is the traditional LR SERDES, the green color is the VSR, and the yellow was the target for the XSR. So XSR still would be lower power, but VSR is kind of in the middle between that and the traditional LR. Now, the problem with that is that the VSR kind of leveled the playing field in the sense that the same interface can be used to drive traditional pluggable optical modules, which means that the same lower electrical link power is available to both CPU and pluggable modules. There's no difference. And one way to deliver these VSR signals is with flyover cables, which in this picture are routed directly from the switch chip to the optical module plugs. Now on this co-packaging side, there's another problem, which is most solutions use external light sources or ELS to make the laser a replaceable module. And unfortunately, these external light sources introduce additional optical coupling losses, which increase the laser power compared to a conventional pluggable optical modules. The net result is that this actually drives the CPU power higher than a pluggable module. How can that be? Well, it's the number of connectors, the optical connectors in the co-packaged solution. In a pluggable module, there's one connector. In a CPO solution with ELS, there's at least, there are typically 4 connectors, and that drives significant insertion losses. Given the fact that there's a very large number of fibers inside the box, one has to sort of assume the worst case here over the life cycle. And besides the connector losses, most likely we also need expanded beam connectors to avoid dust contamination. There's additional splitter and polarization losses. And the net is that the total additional losses are likely to be between 1.8 and 3 dB, which means that the laser power has to increase between 50 and 100%, which drives significantly additional power consumption. So further power reduction is needed. There are ideas including direct drive, which completely eliminates the DSP and uses the SERDES of the switch chip to directly drive the optics. This is challenging to do as a multi-vendor standard, but it does deliver significant power reduction. But on the ELS side, it's definitely tricky to reduce the coupling losses, and perhaps the laser has to move more closely to the modulators again. Alternatively, there could be different modulation technologies that reduce the insertion loss of silicon photonics. That would also help with power reduction. And then, of course, there's the other challenges with CPU, including the overall reliability, serviceability, manufacturability, testability, and the business model. I don't want to dwell on this, but the main point here is CPU is actually not required for either the 51.2T or the 102.4T switch innovation, because the problem has been solved with pluggable optics. And in comparison to CPO, 800 gig and 1.6 terabit pluggable optics have essentially no risk, no design, serviceability, or manufacturability issues. And at least in today's solution of CPO, there is no power saving compared to pluggable optics. So let me sum up my main points here, which are the 800 gig optics modules are in the lab today. They're focused on the dual 400 gig and octal 100 gig breakout application. 1.6 terabit modules based on the 16 by 100 gig electrical interface are next. Those are targeting the 51.2T switch generation, with production perhaps as early as 2023. And then the 1.6 terabit modules that use 8 by 200 gig electrical interface follow them, targeting the 102.4T switch with 200 gig SERDES with an estimated production timeline of 2025. The industry as a whole needs to focus on technologies that drive further power reductions, including the most aggressive process for the DSP, 200 gig Lambda, lower power modulators. Power per bit is definitely decreasing. Unfortunately, module power is increasing due to the increase from 400 gig to 800 gig to 1.6T. And we do need the most robust thermal solution for 20 to 30 watt optics. And my final point is there is an advantage to decouple the optics transitions from the switch silicon because it's the easiest way to innovate on the optics design side and to deliver these new components into the installed base. And with this, I thank you very much.